Recursive Algorithms, section 5.4. So you may be wondering, why did we do all this? Why go over recursive formulas and mathematical induction? And the answer is kind of revealed in those analogies that I gave, like with programming the robot or knocking over the dominoes. What we would really like to be able to do is solve problems recursively. That is, reduce it to an instance of the same problem with a smaller input. So this will allow us to take complicated, large, potentially long time complexity problems to calculate and pare them down to size. And the code, in fact, can be really small for these recursive algorithms. So let's take a look at an example. Let's say you want to compute n factorial. And so you write a recursive chunk of code. That is a function that calls another instance of itself. So it calls, right, the factorial program here, calls the factorial program. But when it does it, it calls it with a smaller input. So we're going down in size, and we have a known solution kind of at the bottom of what we call a wind down and wind up. If anyone has programmed recursively, you're going to run into the scenario where you neglect to have it get smaller each time and you don't have a base case. And this is where your computer just melts. It just implodes on itself because it runs forever. So let's say we want to compute 5 factorial. Well, if we call procedure factorial with an input of 5, it calls, right, to get 5 factorial, it's got to call 4 factorial. 4 factorial has to call 3, which has to call 2, which has to call 1, which finally calls factorial 0. Now, the important thing to note here is that all of these are still open, right? I know we didn't really talk a lot about memory complexity, but here's where it's an important caveat to mention. These are still open on our machines and taking up space in memory because factorial 5 is waiting on the others to report back to it. So this is where we get this wind and unwind, this kind of rope ladder situation. So we go all the way down. It's finally called factorial 0, which is ready to report back to factorial 1. It returns a 1, which returns its results, which returns all the way back, and finally we return back 120. A lot of the problems we've done in this course can be solved recursively. Let's consider the GCD, right? We know that we can get the GCD using the Euclidean algorithm. So if we want to find the greatest common divisor of 14,039 and 1,529, how can we do that? Well, one thing we can do is write a recursive GCD program. You'll note here, looking at the code, the GCD program calls itself with a smaller input, right? B mod A is going to be smaller than smaller than B, because we can see there from the input, it's provided that B is greater than A. And we have a base case, a known solution to work down to. So when we're actually running this code, that is the GCD of 14,039 down to 1,529, we've seen this before. The GCD program can continue to call itself where the inputs are getting smaller and smaller until return 139. Binary search was also a recursive solution, right? It required, we're going to cut the list in half, and then we're going to do the same thing. We're going to look at that halved list and cut it down again. So looking at how this is going to work, right? Let's say we want to search a list. We're going to search the following list there on the bottom of your screen, and we're looking for the number 8. I've decided to make it smaller so it fits on the screenwriter just by referencing list in my function call. So the first time we call this binary search, we pare it down, right? We cut the list in roughly half, and it calls the function again, and it calls the function again, right? Where the list of things it's checking is getting smaller and smaller until that last function call, right? Where my I is equal to my j. In this case, it finds it and it's ready to return 7. That is the position of the integer we were searching for, 8 in this case. Note that my array started at position 1. Finally, let's consider the Fibonacci sequence. Right, this was the recursive definition, f of 0 is equal to 0, f of 1 is equal to 1, and to get to the next step, you add the previous 2 steps. So importantly here, we have 2 base cases. That's okay. Known solutions, there's not much difference having one of them and 2 of them, right? This is similar to our strong induction. However, each time the Fibonacci sequence is ran, it calls 2 instances of itself, each one of them with a smaller input. So let's trace how this is going to run. So if you call Fibonacci 5, it will call Fibonacci 4 and 3. Now, this depends on how your CPU is programmed or how the how the machine language is going to interpret this, but let's just assume, right? Without here, worst case scenario, it calls both at the same time and it's going to keep them both open until the whole thing is done, right? Because then f of 4 is going to call its own instance of f of 3 and an f2, right? Fibonacci 3, Fibonacci 2. What are those numbers, ask? Well, f3, Fibonacci third, to get the third Fibonacci number, it's going to ask what is the second and what is the first Fibonacci number, right? All of these are running independent and, at least with the code we have here, not talking to each other. So we actually see that this tree explodes, and this is why a recursively programmed function is kind of a dangerous thing. Finding out the time complexity and the memory complexity can be very difficult, right? So even a simple code like this, right? Look at how many times it's being opened just to calculate the 5th Fibonacci number.